Here's a question that many people would love to hear your answer to. Again, how do you get quantum physics from consciousness?
Well, that's a very good question. Quantum physics is really an expression of the nature of consciousness. That's why if you understand consciousness, then you can suddenly understand quantum physics, not as a kind of a strange, problematic idea of our reality being probability, but you can understand it from a very basic viewpoint. And here's why. I've said this before, but I want to say it a little differently this time. You know, the quantum physicists think that quantum physics will explain everything, that they can eventually explain everything, in terms of quantum physics, but quantum physics can't explain itself. It explains a lot of other things, but it can't explain itself. It can't explain why at the deepest levels of reality you find probability, not matter. It can't explain the observer paradox. What does consciousness have to do with it? Now, all the founding fathers and everybody else who's an honest scientist realize that consciousness is somehow entangled with quantum physics, because what information is available changes what the result of the experiment is. And we would think that, well, an experiment's an experiment. It's going to work however it works. Doesn't matter what anybody knows. It doesn't make any difference about information. But that's not true. It does make a difference. That's the double slit. That's a big mystery about the double slit. If you know the which way data, you get one thing. And if you don't know it, you get an entirely different result that's not just a little different, but entirely different. So how come that what information is available changes the way a physical experiment works, which should be totally separate from what information is available to the humans? Well, here's why that works. And it also works in the macro world. Quantum scientists say, well, quantum physics just works for little things. It works for the very small and the very small fast things like light and electrons and particles of all sorts. But they can apply it even to the macro world. But mostly they don't understand that the macro world works just like the micro world. And that's because that's the way consciousness works. Consciousness works this way, and therefore the micro world works this way, and the macro world works this way too, because it's all consciousness. This is the way consciousness works. Now, how is that? Well, consciousness is rendering this virtual reality. And when you create a virtual reality, you can only introduce new things into the virtual reality by introducing something in a player's data stream. The virtual reality exists only in the minds of the players. Okay, there is no virtual reality. It doesn't exist in the computer. It doesn't exist on paper. It doesn't exist anywhere except in the minds of the player. There are no little elves and barbarians and Sims characters walking around in some virtual reality someplace, or even in a computer. They're not doing that. That virtual reality only exists in the minds of the players. So that then, by itself, tells you that this is a virtual reality. Now, what comes in, what's available, what information is available to the mind of a player is pretty important. Otherwise, something in this virtual reality can't happen. So the things that happen in this virtual reality have to happen with information going to a player. That's the observer paradox. That's why the observer is a part of the reality, because the reality exists only in the minds of observers, if you will, only in the mind of the players. So that's why that works that way. Now, the other amazing thing that quantum physics says, or that the double slit experiment said, is that our reality at the very root is probability. Well, if you're making a virtual reality, there's only two ways to make it. Well, I should say there's two opposite poles, and you can kind of make one anywhere in between those two poles if you like. But there's two separate poles to it. One is one that I would call from the bottom up. From the ground up, you start with the tiniest of tiny particles, and then the little tiny particles go together and make bigger particles, which go together and make bigger particles, and so on. And you end up finally with atoms, and then you end up with, the tinier particles are the pieces of atoms, the nuclei, the electrons, the other pieces that are smaller. And then you break up a neutron, and oh my, there's more pieces inside that neutron, and you make a proton, and there's piece parts in there too. So the thing is that you build that up from what they call subatomic particles to the atomic particles, atoms, to the molecules, which are bunches of atoms. And then the molecules make physical things. So that's from the bottom up. That's hugely inefficient. You have to know where every particle is. How would you like to have the job of knowing where every electron in the entire universe is at any particular microsecond? That's a lot of reckoning going on to try to keep up with all those things. And what about all the other particles that are small, the pieces of nuclei, the atoms? You have to know where every one of these little pieces is and what they're doing and where they were and where they are now. You'd have to know all of that just to build up a blade of grass that probably has billions, if not trillions, probably trillions of these particles in it. So as you might imagine, trying to build this whole reality up out of little piece parts is ridiculous. It's way too hard to do. I'd say it's functionally impossible. So what's the other pole? The other pole is using probability. Okay, you don't build it up, you just have probability. So all you do in your virtual reality is make kind of images of what's there, and you put those in data and you send it to the players. So the players get that data and they say, oh, there's a tree. Oh, there's a rock. There's another person. So they get the data and they interpret that data. Okay. You don't need to worry about all the electrons. All you do is paint a pretty picture for the players to see so that they can get a sense of what's going on in the game. So you never render anything more than what some player is observing. If the player's not observing it, it's not being rendered. It's just that simple. So when half the world goes to sleep at night, they're just being rendered dreams in a dream reality, but they're not being rendered the awake reality. So anyway, that's much simpler to do in terms of probability. You don't have to render everything, and what you do render is just what's being, measured, looked at, touched, felt, smelt, tasted. All of our five senses. You just render what the five senses are sensing at any particular moment. And that's all you have to render. So that's a whole lot simpler than rendering every subatomic particle in the universe.
And Occam's razor says that the simpler answer is the correct one.
The best answer, right?
Yeah.
So it's obvious that this is going to have to be a probabilistic simulation. Now, when you have a probabilistic simulation, you have a problem that you don't have if you have a bottom-up simulation. In the bottom-up simulation, you start with, let's just call the state vectors of every particle in the universe, all the subatomic particles, everything. You start with every one of them, and then you just have to compute where they are next. Well, they're here going in that direction, so next they're going to be here, and next they're going to be here, and next they're going to be here, because they're moving in that direction. So because you know the state of everything to begin with, you can calculate what the next state's going to be, and the next one's going to be, and the next one's going to be. And materialists and determinists kind of agree with that. Give them the state of everything, and they can compute everything else that will happen exactly forever. Okay, that's a deterministic reality. So, how then does a probabilistic reality figure out what's going to happen next? It doesn't have the previous state to say, oh, here's the previous state and here's where it's going, so here's where it's going to be next. How does it determine what's going to happen next? Well, this is the answer to the physicist conundrum of what's actually really going on when that wave function collapses to a physical particle. Because they know wave functions don't collapse to physical particles. That's a metaphor for something. It's not what's really going on, because that doesn't make any sense at all. A wave function is a piece of mathematics, and physical particles are not made out of pieces of mathematics. So they know it's a metaphor, but they don't understand what it's a metaphor for. What's behind that metaphor? Well, here's how it works. The system, to find out what happens next, takes a random draw from a probability distribution of the possibilities. So there's a whole array of possibilities, and each possibility has its own probability, some more likely than others. A random draw is taken, and most of the time that random draw will draw out one of the more likely possibilities. That's what it means to take a random draw from the probability distribution. It's not just a random draw from all the possibilities, it's a random draw from the probability distribution of the possibilities. So the things that are more likely to be drawn out with that random draw. So it takes a random draw, and that's what happens. Okay, that is exactly what happens. And I've made this analogy many times, but one of the ones I often say is that if you have a scientist with a better telescope, that'll see someplace that nobody's ever looked before, so nobody knows what's there. There's uncertainty. So now they're going to turn that telescope on, they're going to put their eye to it, they're going to look at it, and what do they see? Well, there's a long list of possibilities. Those possibilities are constrained about what we already know about the universe, other places we've seen. So it can't be something that doesn't fit. It has to fit because all those others fit. But then there's, let's say, 100,000 different possibilities that could see out there, gas and stars and all sorts of things, red dwarfs and explosions. There's lots of stuff going on out there that are possible. So a random draw is taken, and that's what they see. So that is the information that researcher, looking through his nifty telescope, sees. He gets that information to his recorder, his computer, whatever it is that's taking that data. They get the data that describes what that random draw drew from the possibilities. So you see, there's nothing really out there. It's all computed. There isn't a bunch of stars and exploding galaxies and black holes and stuff that are out there. They don't exist. They only have to be rendered when somebody's looking at them. And if you look in a new place and you don't know what's there, that random draw from the probability distribution of the possibilities, that's what you get. So nothing's really there. Now, how does this affect quantum physics? Well, quantum physics says that reality is just probabilities. And all those probabilities, or all the possibilities, have probabilities. And when you make a measurement, then you will find a result. Well, making a measurement is the random draw from the probability distribution of the possibilities. That's what making a measurement does. That makes the measurement, and that produces the answer, you see, from all the possibilities. So quantum physics is the way it is because consciousness is the way it is.
Okay.
The reason quantum physics is like that, it's because this is a virtual reality. And in a virtual reality, you have two particular things, both of which quantum physics relates to. And that is, one, information is important. The observer is part of what's being observed, is part of it, because the game only exists in the minds of the players. And the second thing is that what happens next is a random draw from a probability distribution of the possibilities. So that explains why there is such thing as an observer paradox, and why no one really knows what's going to happen until the measurement's made. That's that random draw. That's the measurement. You see, that, well, that's the measurement is a metaphor for that particular action. That's the result. That random draw is the result of the measurement. So now you realize that those things that are peculiar about quantum physics, that make it weird science rather than rational science, are just the attributes of this virtual reality. It's the nature of the virtual reality that creates what happens in quantum physics. But now it also creates what happens in the big world, the random draw that showed that piece of the universe to that telescope. So it also works in the big world. And most scientists kind of think it's mostly just good in the little world of tiny things, but they realize they can express the same equations with big things, but it doesn't really seem to work exactly the same here, because the wavelengths get to be so small and the frequency so high that it turns into things that are physical-like, which of course is exactly what's supposed to happen. So quantum physics is easily understood if you understand that this is a virtual reality in consciousness, created by consciousness, and that they require the database, which is what the Hindus called the Akashic Records. That's their name for this database. And because that information has to go through the mind of a player, and the fact that the reality has to be based in probability, otherwise it can't really be done. It's too hard to do it any other way. So there's this mechanism for seeing what happens next. So you see, quantum physics is just a representation of the nature of our reality as a virtual reality based in consciousness. Now, we work in the physical world, and our physical world works exactly the same way. And I was talking about this a couple of weeks ago with some people, and this was the example that came up. That is, you have red and blue balls, and you dump a bunch of red and blue balls, about the same number, into a box, but you don't know exactly how many of each color go in there. So you just dump a bunch of it in, but roughly the same number, not just one or two of these and hundreds of the others, but roughly the same amount, but just roughly, and you throw them in there. Now, nobody knows how many blue and how many red balls are in there. Okay, the box has now been sealed. There's uncertainty about how many red and how many blue are in there. Okay, now this is a macro experiment. This has nothing to do with tiny little things. So the only way to find out would be to make the measurement, to go in and count all the reds and all the blues, and then that's what the wave function would collapse to, whatever that number that you got. Okay, of course, there's no wave function here. There's no wave function. There's just a bunch of colored balls in a box. We don't need a wave function. All right, so now what if somebody used their intent to increase the number of blue balls? They just had an intent. There's more blue balls than red balls. And let's say you had several people who knew how to do this sort of thing, who had developed their intuitive sides enough that they could do that. Well, when that measurement was made and a random draw from the probability distribution was going to say how many blue balls are in there, that would be a little higher number, because you've modified the future probabilities a little bit with your intent. You see? So the probability that you're going to have more blue balls will go up a little bit. The count of the blue balls would go up. All right. And if you had people doing the same with the red balls, let's say they wanted more red balls to be in there. If you had people who had, some ability to use their intent to modify future probability, you could find there were more red balls, either one. Now, a materialist would say, nonsense. The number of red and blue balls in there has been determined. When the balls stopped dropping and the lid was slammed shut, there was an exact number of each in there, and that can't change. But of course, you could do this experiment, and you would find that, there could be, let's say, 5 more red balls than blue balls, but you want more blue balls. So you might make them go up to be only one more red ball than blue balls. You see, it doesn't mean you're necessarily always going to get the answer you want. There still might be more red balls, but only one more rather than 5 more. See, so you bias a little bit. So that means that your effect is always covered up. You're not really sure.
Consciousness brings matter into this physical reality.
Yeah.
Like the man researching an area of the stars and finding that bit of information, what that is there. He brings it into this reality then, that's fixed. That's
That
brought into this
stays. Once it
reality.
comes in, once you make the measurement, it's here. Okay. Now, making the measurement has to come in through the mind of a player. That's a player observing something, connecting with something, measuring something. So anyway, this, you see, is quantum physics at the macro level. But generally, that's not considered possible in the way I just described it. It's like that because the number of blue and red balls there, the physicists would say they're in a state of superposition. It could be, anyway, we have uncertainty. We don't know how many there were. And as long as there's uncertainty about the outcome, then there are 2 possible outcomes there, more red than blue and more blue than red. That's the 2 possible outcomes. Now, which is it? Well, you can bias that with your intent. That's the same thing that, Pear Labs was doing that same thing. It had random number generators that were created by decaying particles, by radioactive decay. So these are called natural random numbers. They weren't contrived in a computer with a seed. They were picked right out of a random decay. And there's other ways that you can get what they call, real randomness or actual randomness. They have some names for that, and they were able to bias those so that if they got 100 random draws, the average of those should be, let's say if they were between 0 and 1, then the average should be a 0.5. Or between 1 and 2, then they get a 1.5, whatever. They get the average of this randomness. And they'd find out, of course, if you only do 100, then you're not going to get exactly 0.5 with 100 zeros after it. You're going to get a 0.49999 or a 0.50002. You're going to get something because there's just 100 of them. Now, if you did 10,000 of them instead of 100, then it would be even closer. Now you'd get a 0.5000001. Or a 4.9999999 because you started with a lot bigger sample, therefore it's going to get a lot tighter fit to an average. But within however many you do, there's some uncertainty. You're not going to get 0.5 with 1,000 zeros after it. This is not going to happen. Things don't work like that because there's randomness in it. These are random numbers. But they found that they could bias those numbers tremendously so that the next 20 random numbers that came out from this radioactive source all were 0.5000 something. Okay, they all were just slightly on the high side instead of the 0.4 or 9999. They were all a little on the high side. Well, that's just good luck if you do it once. But if you do it 10 times in a row, that then is the same as flipping a coin 10 times and getting ahead every time. And that's very unlikely for that to occur. And they were not only doing it 10 times in a row, they were doing hundreds of times in a row. They'd have a little robot that was made to go forward, backward, right, or left, the same amount, randomly. And if they gave these same real random numbers to it, that little robot would just sit there and dither around in the center of the table, and they could wait for an hour. And that robot an hour later was still just dithering around at the center of the table. So it was very accurate in the fact that it only moved one of those directions and it moved a precise amount always. So it could dither for a long time and still stay right in the center of the table because it went left, right, forward, backward, equals amount randomly. Then they'd have somebody come in and use their intent to modify those random numbers. And that little robot would dither around, and they go out and fall off the edge of the table. I've seen that in videos from Pear Labs. It's just one of their experiments. And how did it do that? Well, it came up, 0.50, it came up on the high side too many times in a row. And when it did, all those, say, moving to the left, added up, it fell off the table. So yes, that's the same sort of thing. You see, that is in the macro realm of taking averages of all these numbers. They could use their mind to bias these random events a little bit, so that when the measurement was made, that is, you watch the robot and see what happens, the measurement's made, it falls off the table because of the biases that it has been given. Thousands of tiny little biases, all in the same direction to make it eventually fall off the table. So that's like flipping a coin 10,000 times and always getting a head, or getting, a whole lot more heads than tails. Or in this case, there were 4 different directions. So, it's very unlikely that would happen, and very unlikely that it would happen whenever the person sat down and met their intent to it. And if the person wasn't giving their intent to it, it just stayed in the center of the table. So they did literally hundreds of these kinds of experiments. That little robot was just one of them. I happen to remember that because I saw the movie of it. And they did hundreds of these experiments in all kinds of different ways. And at the end, they decided that they computed their their level of significance. In statistics, you have this significance level you can compute. And generally, if you get a significance level of, say, 0.9, that's good. 0.95, that's excellent. And anything over 0.95, it's almost a fact. That's really good. 1 in 1,000 is a pretty high. You only have one chance in 1,000 that you're just a lucky guesser. That's basically what that means. Well, they had their computation of their level of significance, and it was like 1 in, I think it was 5 billion, that they were just good guessers. And just by chance, the robot just went off the edge, or the other experience it did. The robots just was cute. That's probably not their best experiment, because that's a mechanical thing, and there can always be little wear and tears and things going on in mechanical things. But that was just one of their things that they did just because it was impressive and fun. But they had a lot of other ones that didn't have any mechanical parts to them at all to wear or mess up in any way. They didn't have any, consistent biases that would add up like that. There was no room for bias. But anyway, see, so it's been done in the world. It's been done scientifically. But at Pear Labs, what happened is they said, yeah, but those are just little tiny differences. So it really doesn't matter that much. The 0.500001, that's so small that we can neglect that. Well, in and of itself, that would be true. That's just a very small difference. On the other hand, to get that 1,000 times in a row, or even 10 times in a row, that's flipping the coin. That's 1/2 to the 10 power. That's a very, very small number. So that's the point. We've measured this. It's been good science. We know that it works this way. I've never known of the experiment with the red and blue balls. I just made that up on the spur of the moment. But that is quantum physics at the macro level. Where there is uncertainty, then the answer is unknown. That's what uncertainty means. It's unknown. If it's unknown, then there are multiple possibilities. Those multiple possibilities will be chosen by a random draw from the probability distribution of the possibilities. Okay? So you can bias those probability distributions with your intent. So that's how that works. And it works in the macro world, it works at the micro world. So all of these things that basically look at uncertainty and say that the resolution of that by a measurement, the measurement could get one of several things. And each of those have probabilities. And one of them, just one of them, will be what the measurement says. And that's the scientist's idea of a probability wave collapsing to a physical particle. That's how they describe that, which of course literally is nonsense. But as a metaphor, it's not a bad metaphor. It kind of seems that way. So I just thought I'd give a little demonstration here
Thank
of
you.
why the world is the way it is. It's because it's a virtual reality based in consciousness. That's why. Because in a virtual reality, every change has to come through the mind of a player. And because the only way to determine what's going to happen next is by a random draw from the probability distribution of the possibilities.
Yeah.
And because of that, if you understand consciousness, then quantum physics is simple. You know exactly why it works that way. It couldn't work any other way. That's the only way it could possibly work. So it's not really a big, strange mystery. And the things like the paralab's done, oh, well, sure. Of course they can do that. They can bias those particles that are, shot out of the nucleus, of a radioactive source, such that they just go to the high side, the average of them, or to the low side a little bit based on their intention. So all of that is all wrapped up in the nature of consciousness and virtual reality. So I thought that maybe had a little bit of new nuance to it. I've said a lot of those things before, but I thought this was maybe a little better way to explain.
Much more elaborated on.
So it's not that quantum physics is the reason why reality is the way it is. It's that quantum physics is the way it is because of the nature of reality.
Yeah, how fascinating.
And the same goes for the entanglement is the same sort of thing. Well, in our physical world, that entanglement seems ridiculous. How do these particles that are entangled, then you get moved, how do they, one changes, the other changes instantly? Why is that? That's weird. Well, from the consciousness computational viewpoint, that's not weird at all. You've got two particles, and let's say the sum of those particles, momentum, has to be a certain value. Well, that's just a fact. That's a conservation law, that the momentum of the two particles that go out is equal the same as the momentum that came in with a single particle that then turned into two particles. That's a conservation of momentum. Well, that's a fact in computation. It doesn't matter how far apart. There is no how far apart in computation. In consciousness, how far apart doesn't exist. All it is that when this one changes, that one's going to have to change because the total momentum has to be this, the same as what came in. Conservation of momentum, conservation of energy, there's lots of conservation laws. And those conservation laws say that in this computation, in order to maintain that conservation law, which is kind of central to the symmetry of the universe, when one changes, the other changes, and they're entangled. And for us, that's a big mystery. How can this affect that? Because not even translating at the speed of light can one communicate to the other. It's instantaneous, and that's this weird science. It's not weird at all if you look at it from a computational viewpoint. It's just a fact. If this, then that. If this spin up, then that spin down. Because the system had a zero spin. So now if there's a spin up, the other half of it, if it one particle breaks into two, the two particles are entangled because they have to abide by conservation laws. And it's just a computation. It's an if-then statement. If this one's up, that one's down. If that one's down, this one's up. And when you run through a program, it's just real simple because inside that program, there is no space. Space is made up by saying, here's a point, and we'll call that the origin. And now we're going to put three mutually perpendicular unit vectors, and that will define all space from minus infinity to plus infinity everywhere. It's all defined with those three unit vectors. Space is a computed thing. You see, it's not something that has to do with reality. It's a computed space, just like the computed space in Sims. Those Sims characters walk around in space. They have open doors to go into houses. They get in cars to drive around. There's space there. It's computed space. Our space is computed just the same. It's not a fundamental thing at all. Time is fundamental. Space is computed.
Was what you were describing that there is no distance where this happens, that happens, was that Einstein's spooky action at a distance?
Yes. Yeah, and Einstein was slow to come over to that viewpoint. He initially said quantum physics is not right. It can't be right because God doesn't play reality
Dice.
with dice. He doesn't play
Doesn't
dice
play
with
dice with the
reality.
universe.
Okay,
Yeah.
that the universe has to be a fixed thing. You know, there has to be so many blue balls and so many red balls in there when it's sealed, and that's it, and that's the number, and it doesn't matter what anybody does. When you open it up, those numbers will be whatever it is that they were. You see, and quantum physics said, not the case, actually. You don't know what number is, and that's up for grabs until you make the choice, and then you'll get one thing or another. But there are these other possibilities, and you have to consider all the possibilities. And Einstein said, nonsense, doesn't make any sense. But then when entanglement was a thing and it was proven and in the lab and it worked, then Einstein said, okay, guys, I was wrong. Now let's go work on quantum mechanics. And after that, he became one of the forces in quantum physics as well. But he initially didn't think that that was possible. So he was a little latecomer to the party of quantum physics, but once he got there, he was good as usual. You know, he made his own contributions and worked on it. That's when he started working on his Tao, you know, his theory of everything.
Well,
So
thank you for
anyhow,
this. Thank you
that's
for
kind
this,
of a
Tom.
little history.
No weird physics in my big toe.
No, no weird physics in my big toe. There's weird physics out in the physics world, but it's not really weird at all. It's
Not weird.
perfectly understandable and
Yeah.
perfectly rational. It couldn't be any other way than the way it is.
Mm.
And it was easily predictable that quantum physics would be the way it is long before there was quantum physics, if people just understood that consciousness was fundamental. Once you get that, then understanding how these things work is simple and elegant and
Sign of a
requires
good theory.
only one assumption, you know, that all just falls out very naturally.
Thank you, Tom. Beautiful. Thanks. Would you like to see a better world? Get a better perspective. Balance your intellect with intuition and explore your true nature with the Exploring Consciousness and Everything Paranormal program with Thomas Campbell. In this program, you will have the benefit of Tom's vast experience and learn to access point consciousness, communicate with the larger consciousness system, remote view, use your natural ability to heal with intent, and explore reality in the out-of-body state. His famous binaural beats are included. Details are in the description below. Thank you.